talking about quantum lambda calculus. Hello everyone. My laptop's a little slow, so just give it a second here. So quantum computing is a fascinating area of research, but a very difficult one for many people to approach because it's so specialized and for, anyone except theoretical physicists, the language of quantum computation has historically been inaccessible. Up until fairly recently, everyone has been forced to use Dirac notation, and that is a very dense but succinct notation exclusively used in quantum mechanics for describing objects in superposition, etc., etc. And it's a very powerful notation, but again, it supports quite a lot of features and is very, very dense. So when you're thinking about quantum computation, obviously it would be nicer to think about it in terms of computer science. And one of the most natural languages for describing quantum computation turns out to be the Lambda calculus. So obviously, one of the most well-known features of Lambda calculi in general are functions as data or higher order functions. So code and data is primarily treated equally. You can pass them around just as you would any piece of data, like a bit or a string. And also, it creates a nice closed environment for the code so that it's treated as a black box, an atomic, instead of as something that you can rip open and get at the internals of. And pure functional programming, you don't want the internals to be exposed. You want everything to be neat and tidy and properly modular. So in terms of the quantum lambda calculus, that offers a familiar and rigorous syntax for computer scientists to start thinking about quantum systems, at least as they apply to quantum computing. So that you don't have to get into the full standard model and the notation of it to understand how to even approach the subject of quantum computing. And the quantum lambda calculus specifically, presented by Selinger and Valiron, it supports all high-level programming constructs, and was designed exclusively for quantum computation and not just adapted to it because there's nothing better. So what is the quantum lambda calculus? It's a strongly typed lambda calculi. It's a call by value language, so everything has to be evaluated before it's passed to its function. It's inherently lazy, which is very useful for quantum computation. And it's a higher order quantum computing language, obviously. And it's quantum Turing complete, which is a very specific constraint, very similar to Turing machines for classical computers. So when you combine higher order functions in quantum phenomena, you get some very interesting things, properties that you wouldn't normally think of, and nobody had thought of until Selinger released the idea of entangled functions. Also, if anyone has any questions, wants to stop me, just please feel free. Yeah. Quantum Turing completeness in more detail compared to classical Turing completeness. You can't hear me? Okay.
Yeah.
Is that better for everyone? Yeah? So quantum Turing completeness is a set of constraints on the mathematical structures that are computable in a quantum system and prevent basically unbounded equations from happening. And it also ensures that, there's all the properties you need for complete computation in a quantum system that would equal classical computer, like loops and functions and data types, et cetera, et cetera. It's supposed to be feature equivalent. The additional features of quantum computers are mostly concerned with how do we do what we're already doing, but better and faster. But some properties of quantum systems are, of course, impossible in classical computers, in real time anyway. They can be simulated, but at an exponential slowdown. So since the quantum lambda calculus is strongly typed, it does have some types built into the language. The types that come right with the syntax are, of course, classical bits, quantum bits, and higher order quantum functions, which normally appear as either classical-like functions on quantum data or pure quantum functions. The classical bits you know and love, they are the same as on every other computer you use. No surprises. Has to be either a 1 or a 0, no magic, other than the usual digital wonder. Some important points to note, though, is that you don't normally think about it, but classical bits can be duplicated endlessly, and that's kind of a property of digital information. And you won't see that in quite the same way in quantum systems. Qubits are a very different beast. I'm not going to dive too deep into this. I'm just showing it here for completeness. But a qubit, it isn't a fixed value, either a 1 or a 0. It's a state vector with probabilities attached to each possible state that exists within this space. And those are the equations to calculate what the probabilities of the possible values are. But you can think of it as just a linear superposition of these basis states. So out of everything that it can be, it's just all of them together side by side in a vector. So for qubits in the quantum lambda calculus, you actually have to prepare them every time you want to use them. Unlike the classical bits, which you can just copy every time you want to effectively copy, you would have to measure it and then create a new instance of qubit. Qubits do support some interesting properties, though. They are all unitary maps, which means they can be defined by their identity function. They have measurement as a primitive operation, otherwise you would not be able to use them for computation. They exist in superposition until measured. They can be entangled with each other, and they can be teleported, and they support superdense coding. Yes? typically quantum computation happens in cycles of classical computation and quantum computation. So you would have a classical interface, and then you would write your software with it, and then you would send a program to the quantum processor, and it would do all its work, and at the very, very end, it would measure everything and give you back value to the classical output. So this is actually what's called the circuit model, and it's always classically interfaced. So everything has to be measured before it gets back, but technically all the quantum computations happen simultaneously. Does that answer your question? Yeah. Yeah. Sorry?
So this equation there, u times u is u times I.
Yeah, so this is just to say that, like, you know, it's commutative. Like, that one is the same as that one, and that's the identity. Right?
What are the It seems cracks.
Yeah, it's category theory stuff. It's,
Okay.
yeah. It's important to mention.
Assume some kind of map and then stars the adjoint or something like that. So
Mhm.
the transpose of this map composed with its, there would be no form the same as the other way it is the other. But yeah, I don't think it's getting terribly useful.
Yeah. Yeah. So back to the functions. The classical-like functions, again, this actually ties into your question. These are written and exist entirely on the classical interface, but they do operate on data that may exist only within the quantum computer. So these functions, they only act on quantum data. So they still, require the state preparation and so forth. And they behave as classical functions. They can be used over and over again. And they can, of course, be functionally pure, or they can be destructive. And otherwise, they, behave as you would expect them to. No real surprises. Just the added ability of acting on quantum data instead of just classical data. Now, the pure quantum functions are a little tricky. Because they are actual stateful quantum objects, they can only ever be used once. So you can't really think of the pure quantum functions as classical functions. You have to think of them as more like functors in the computer science sense, not in the category sense, or as an object that has to be instantiated in OOP.
So does that mean that your type system is going to end up having a linear logic aspect like linear type aspects?
Yes, and actually that's one of the reasons why the authors chose to use intuitionist linear logic in their paper, to simplify the description. In order to complete an evaluation of these pure quantum functions, you then have to measure them, and that also destroys them. So that's why they can only be used once. But you can think of them as quantum states with an interface, and that gives you this nice little black box closed world. Yeah?
So it seems like there's lots of state that is going on here.
Mm-hmm.
I mean, you said that you can almost think of them like objects. So in what sense are they pure functions? Because when I think pure function, I think of something that really is not like this at all. It's repeatable and all that stuff.
They're pure in the quantum sense more than in the functional sense, and this is the terminology that's used in the paper.
So is it that it is purely quantum, like the data
Exactly.
that they? Yeah. Okay.
Yeah.
Purely quantum as opposed to.
Yeah.
Right.
And yeah, I mean, instead of just calling it function every time, he sometimes uses function object to distinguish it from the classical, side-effect free pure functional functions.
So the ones on the previous slide were like.
Functionally pure, yeah.
Yeah,
Ideally. But the other cool thing about these purely quantum function objects, we'll stick to that term there, They actually exist in superposition until measured. So that means that the function is actually all of its applications simultaneously, all of its possible applications. So for, a really complicated function that could, think of any function you would normally write, add any two numbers together, it's actually technically calculating every possible number that you could ever add together with it, if you have a big enough, computer to actually evaluate all those states simultaneously. So now for the actual syntax. I won't spend too much time on this as it's somewhat dense and specialized. But just so you're familiar with it if you're interested in reading the paper more. Obviously, the term constants are the built-in operators, the special forms as they're often called. And it has pretty simple semantics. The primitive operators are new to prepare a state, and typically you pass it a 1 or a 0 to prepare a single qubit. However, you can also use the custom data types that you define in the syntax of the quantum Lambda calculus to prepare multiple states at once. And then measure, you pass it a quantum object of some kind, and then it returns the classical value. And then you have the set of unitary gates, which are ported over to the quantum Lambda calculus from the gate model. So just to explain those a little bit better, quantum gates are very similar to classical logic gates that you would find in normal processing. The difference being that they operate on, quantum states and not, just flipping bits. Then you have the term variables. So, you just set a value to a term variable, such as setting x to the qubit produced by nu 0. And this is how you define a function. This can be used to define either type of higher order function, and it operates much the same as it does in the classical Lambda calculus. And this is the application of the function m to the arguments n, and in this case 0 is the argument and m is the function. This is a pair or a tuple. It's useful to have pairs of qubits in many of the quantum algorithms.
So your function definition, you let x to n, which is a rate, which is a set for both here is a set for
Um,
2 slides back.
Sorry, I couldn't quite hear you.
If you go
Slides
back
back.
2 slides.
Yeah.
It's function definition.
Yeah.
N is a set for
M could be any other form of the quantum Lambda
And
calculus.
it's just kind of the body of the function.
Yeah.
Like any expression.
Yeah, the three grammar variables I use are m, n, and p. So those could be any expression of the quantum Lambda calculus. And there's just 3 because that's the most number of terms that appear in a single definition. This is a convention of BNF grammars.
So for that example, the identity function, the lambda x is saying, give me an anonymous function that takes a parameter x, and then the body of that function is going to be returning the value of x.
Yes.
Does that make sense to you?
That's the identity.
That's for the identity function. That's exactly what it is. So m is the body, and For the identity function, it just returns itself. Yeah.
When you have a pair of qubits, does that minimize the number of possibilities that the quantum computer has to go through? Like, does it become faster?
I mean, yeah, they all kind of get evaluated simultaneously, at least in the ideal quantum computer. They're expected to. So because they're in superposition, they're just, you do the square of the number of qubits that you have to get the number of total states.
Thank you.
So yeah, the pair is just, like a tuple. It's just a primitive data structure. Yeah.
So, sorry, just to clarify, whenever we see a capital M, N, or key,
Mhm.
so we should think of that as being both a qubit, but also any form in the language.
It could be any expression defined in the grammar, or by an extension to the grammar. So this tuple, this pair here, doesn't have to be 2 qubits. That's just one application of it. But yeah, it could be 2 functions that are in a tuple, because functions are first-class objects. And that's the unique 0 tuple, which is equal to Lisp's nil. I couldn't find a good asterisk in any of my fonts, so I used this stupid star. Sorry. This is lexical binding, although it's a little different in the quantum lambda calculus. And I had actually a bit of trouble explaining it to Dan and Leo last night. But essentially, what it does step by step is that it first evaluates M and returns a pair, V and W. Then it assigns V to X and W to Y. And then we actually covered this in great detail at CompSci Cabal. But the derivation is really long, so I don't want to spend too much time on it. But basically, it controls the order of evaluation, whether you start on the left, whether you start on the right, and how efficient the evaluation is going to be based on how it's evaluated. Keeping in mind that it's fundamentally lazy, and it's a call by value. This is a case statement on a disjoint union, and it's also pretty dense to explain. But you can think of it as a switch in Python or a case statement in Lisp. How many people are familiar with those? Okay. Anybody want?
First matching.
Yeah. Yeah.
All the just have this.
Yeah. Okay. Yeah. So if you're familiar with MO as well, then it's. And this is how you define recursive functions. And these are named as f in this case. These are named as f in this case.
Is there a reason why you specifically have a separate recursive domain from the regular
He does not distinctly explain himself in the paper, but I assume that there is a reason. He doesn't just use the identity function of any object as you normally would expect to.
Just interested if there was
Yeah,
justification.
if I had to guess, yeah.
It's a controversial issue, right?
Yeah.
Standard ML omits this form and OCaml permits this form.
Mm.
And there's some justifications about whether you want to shadow things by default or not. But I was thinking it's something that should be as abstract and pure as someone's modified lambda calculus. You
Yeah.
think that such considerations would be irrelevant. Just create new names where you need them.
Yeah. This is one of the more contentious terms actually out of the quantum lambda calculus, along with the need for the right and left inclusions. And also the lexical binding syntax. Yeah?
Okay, so recursion in quantum mechanics, does that mean it goes between phases of classical and quantum computation? Or is recursion all in one quantum step?
It can do both. So you have to think of recursion in different ways. If it's a classical like function, then it is going to loop through the classical interface. And actually Shor's algorithm works that way specifically. But some of the quantum algorithms that are rigorously defined already, they are recursive in a purely quantum sense, and they don't have to be measured to produce the expected output.
So for every level of the tree of recursive calls, do you need like more quantum storage? Like more qubits? Or they don't be done in one set of qubits, one vector?
Well, it depends on how you write the function. You could write both, actually. And I think it supports both. Yeah. So, again, that would be the difference between, how efficient you want your code to be. It'd be like forgetting to tail call optimize. Obviously it's going to crash your computer, right?
You like quantum RAM?
Yeah. And the paper describes many ways in which the quantum lambda calculus can already be extended just off of their research. It already supports infinite data types, as well as the fixed data types such as vectors and arrays and qubits. They describe quantum closures in quite a bit of detail in the paper. They present different approaches to teleportation and the literal inverse algorithm that allows for superdense coding. And they cover value states and error states. Now, an important thing to point out about the value states is that I mentioned earlier, you can't really think of pure quantum states as having any value at all. The value is something that you get when you measure a quantum register, or like a vector of qubits. So the value state is a very specific term for the expected classical value of a quantum register. And obviously you can't expect all of your quantum computations to be successful, so the paper also provides an extension to support error states, so that you can actually catch any errors and handle them properly. Yeah.
How does a quantum error state work? Because if it doesn't actually, like usually an error is just simply another value, or perhaps failure to calculate the value. So how does that work in the quantum computer?
It works in a fairly similar way on the outside, as far as the interface is concerned. It does return, an expected value, which is not used for anything but errors, right? So like an error code, or I believe the definition in the paper was a modified version of the zero tuple. So it's a special case for handling errors. And the paper finishes off with some ideas the authors had to get to a concrete model or implementation of the quantum lambda calculus, so they could actually start programming with their cool new formulas. And true to their word, they released the Quipper language, and this is it. It's implemented in Haskell, and it includes, among other things, an actual quantum computer simulator.
So that means that you can actually run this on a regular non-quantum existing computer.
Yes. The simulator runs in exponential time. So as the quantum problems become more complex, it becomes more and more difficult to compute any of the quantum problems. And that is a physical limitation of classical computers. But it's still really, really exciting to see real quantum computations in action, even though it's on, your MacBook and it's overheating because of it. Yeah.
What is Hadamard?
The Hadamard gate is one of the fundamental gates for universal quantum computation. So it's one of the gates you absolutely have to have to achieve quantum turn completeness. There's actually an interesting list of the gates that exist, and it shows 3 different models that allow for arbitrary combinations of the gates that support all quantum computation, but you don't actually need physical implementations of every different type to actually achieve it. So with a subset of 3 gates, there's like 3 sets of 3, you can achieve all quantum computation without needing physical implementations of any one.
So is that similar to classical and or not XOR gates?
Precisely, yeah. So you choose your subset, you implement your architecture, and then you get all quantum computation for free. And it's a matter of what architecture you prefer, really, which is easier to physically build. But the Hadamard gates are actually an art, because they're a really, really important gate. And another gate that is almost always used, but not, it can be replaced by the Toffoli gate, is a controlled NOT gate. And you actually saw that in the first slide on the quantum circuit diagram. It was the little circle plus on the circuit.
Could you just elaborate a bit more? Like, so what is this Hadamard gate doing? Is it creating a quantum state or anything?
No, it's
What
that qubit there is being passed to the Hadamard gate, and then it's being assigned again to Q, right? And then that pair is being measured and then assigned to X and Y, and then X and Y is returned as
Well, I
two
sort of
possible
meaning more
ones.
like an AND gate that's clear, like you AND them together and you get
Mhm.
something out. Like, is there some sort of understanding or explanation?
Yeah.
Quantum gate?
You can define all of the quantum gates as matrix multiplications.
Okay.
So the Hadamard gate is a very specific matrix multiplication on the qubit vector state that you pass to.
Oh, okay, so you have your input state.
Yeah. So you're inputting the entire qubit, right? So it's a matrix multiplication on every possible state in the qubit state vector.
So I guess the thing with the advent that was talked earlier is telling us that all of those unitary, all those gates are inverted.
Exactly. Yeah, they're all unitary. They have they're variadic in their arity, but they're all unitary in that they, in terms of categories, they're in. So they're fully invertible. So you can change the order of those gates, and then at the end you'll still get the same result.
But the gate has to, the reason they're Hadamard gates is they're unitary. The unitaries are, so the unitary gate, it has to add up to 1 for probability of 1. That's why it's unitary. The adjoint is a complex number.
Mm-hmm.
And then when you square everything, you add all the probabilities for each state.
Yeah.
That's come up to 1.
Yeah.
So that's, the Hadamard is just guaranteed.
Exactly. Yeah. Any other? Yeah.
What is this CIRC, CIRC?
The circ is it's like a circuit lifting operation for Quiver. So that's telling it that it's it's a monad. So it's like lifting the bits to the output. Yeah.
Okay, so why does everything return a pair? Everything returns, like when you're measuring it, you're always getting X, Y, and that, right? Ones and probability is 1 and 0 or something like that.
Well, if you want to return a pair, you can, and in this case, in the first one you are, but in the second, you're only returning a single qubit.
Okay, so if I didn't measure the Q, it would just return 1 value. So 2.8, 1.
Yeah, and typically if you just want one measured value, then you just return the first value, but a qubit has at least 2 states, at least 2 distinct states. So you could want both of them, the value and the anti-value, right? So if you're measuring, in this case, this pair is not, that specific case for superdense coding. This case is 2 entangled qubits, right? So you want the values for both entangled qubits. Yeah.
Just, so if the authors are going to go and implement this monadic syntax, why do you think they bothered with the lambda calculus as the basis for their abstraction in the first place? It seems to me like they just wanted, if they're going to create very imperative monadic code, like why bother? Any thoughts on that?
I have lots of thoughts on that, but I don't want to criticize them because they did put a lot of really hard work into this project, and they made a lot more progress. Yeah, it would have been nice if they followed a syntax more in line with Lisp languages. Anybody who knows me knows I'm a bit obsessed with Lisp. So I would have preferred that personally, and a lot of other programmers I think would have as well. But if you read the paper carefully, you will see that Haskell is deeply embedded into it from the beginning, and they were thinking in terms of categorical semantics as it appears in Haskell from the onset. And they really, really wanted a monadic interface. It made them happy, I guess. Any other questions? Yeah.
You mentioned the Dirac notation at the beginning.
Yes.
And I sort of think the way you presented it seemed like it was preference to go towards lambda calculus as opposed to Dirac notation.
Well, the preference is to go towards syntax that's familiar to computer scientists as opposed to syntax that was designed for, the whole field of quantum mechanics.
So the follow-up then is, like, would it be possible to write what's happening over there as Dirac notation?
Yes. It would be about twice the size though.
Okay.
To write it all out. All these operations can be expressed in, most mathematical formalisms, but Dirac notation does. It's directly translatable to linear algebra, but you can also extend it to support like category theory, I saw a really weird use of Dirac notation for, we were talking about it a few weeks back. It'll come to me later. But yeah, it can be applied to many fields. So, Dirac notation is very flexible, but it's just very specialized. So their aim was to create a language which should look more like something computer scientists will just accept, to bring it, down to their world, instead of forcing them to become physicists just to understand quantum computing. Because quantum computing, even though it exploits aspects of physics, it's supposed to be, and Feynman, when he invented it, originally pitched it as just computation that's leveraging more physics than it used to.
So in these examples here, you mentioned there's classical functions and quantum functions.
Mm-hmm.
Do we have those here? It's hard to interpret.
Yeah. These are. These are both. Yeah, these are both.
This
yeah.
one kind of looks like maybe a classical function, taking qubits and returning.
Yeah, these are, these are all pretty much classical-like. You could probably treat them, no, there's no state preservation. Yeah, these are all the first type. These are all the first type. Yeah, so basically what this piece of code here does is, Alice has these two qubits, and she sends one to Bob, and then Bob wants to know what it is, and then if one of them measures it, then the other gets the value. It's a standard algebra problem. Any more questions?
So-
Interjections? Sure.
So earlier you said there's purely quantum functions.
Yes.
So how do you write those down?
Well, those are written with the quantum closures. So I didn't introduce the syntax for that because that's later in the paper and quite extensive. That's part of the extended QLC, but it's supported by the native syntax. But if you actually take a look at the Quipper documentation, it's a little more straightforward. At least in the Pascal, at least.
So this purely quantum function sort of loses this looking like a regular function aspect?
Sorry?
So when you're writing down these purely quantum functions, they kind of lose this looking like a classical function property?
Yeah, I mean, because you're writing them, in a quantum closure, so there's this like local state that you're giving to it.
Oh.
So you have to explicitly define this, quantum closure to create this new scope, and then if you assign that to, a function definition, then you get your quantum function as a purely quantum function object. Okay? Yeah. Anything else? Any more questions? No? So I'm not going to talk too much more about Quipper. I just wanted to introduce it because it exists, and that's cool that you can already use the quantum lambda calculus. If I didn't already say, it's an embedded functional language, obviously built on QLC, implemented in Haskell, and funded very heavily by DARPA, which is like DARPA but funded by the intelligence community. Now, when I first discovered Selinger's work, an earlier paper of his actually, that just introduced his ideas, my first idea was, wow, I can't wait to implement this in Lisp. I didn't even think about Haskell, I just put straight to Common Lisp, and that's what I wanted, was a quantum Common Lisp. And in the earlier papers, it didn't seem like it was going to be that hard, but that was before the paper that I actually went through today. So, a few of the challenges that you face when you want to port the quantum lambda calculus is that you need, support for the type lambda calculi. You need categorical semantics. So, monads, monoids, functors. Provable mathematical purity. Outside of Haskell and the ML family, it's not as easy to implement those as you'd like to think. The quantum lambda calculus also has a fairly large grammar compared to Church's original lambda calculus. And also, quantum computing kind of requires some concurrency, and you don't want to have to manually program that concurrent operation into your system. It's more convenient when it's just there, so that it behaves as you expect it to. So my project, Blackstone, is an attempt at a quantum common Lisp. And again, it was based off his earlier work as I started it, before he got heavily into the type theory and the other aspects of category theory. And I assumed that it would be no problem to do a dynamic typed quantum lambda calculus. And I really, really wanted, to say, let's step back from the idea of these purely quantum function objects, and let's actually have quantum states.
Just try connecting again. Let me know if it doesn't work.
My laptop appears to be frozen. Sorry, guys. yeah, as I said earlier, it is kind of difficult to adapt the quantum logic calculus as is to Lisp family languages, as they did have the intent for using this monadic syntax in the final product, and they seem to want that, and it is one of the aspects that I think is holding me back, because it works fine in Haskell, but not really so much anywhere else. And yeah, my progress on Blackstone has been relatively slow. They have a huge team at Dalhousie University, and I've been working by myself on this in my free time. But it is has been a fun project actually working on a quantum computer simulator in Lisp. Other than the people at D-Wave, no one else has accomplished that. But this one is, of course, a lot more. It has a much larger scope than what the D-Wave machine was meant to do, as its full gate model simulator. I'm trying to reconnect again. It's responding.
How are you finding the concurrency aspects? And are you taking any inspiration from like earlier concurrency-oriented Lisps like Star Lisp or Termite or anything?
In practice, I use L-Parallel on a regular basis. It's one of the more stable concurrency libraries. But I would like to see McCarthy's QLisp implemented into like the Common Lisp standard as a whole, because it was kind of ignored during the standardization process, and that's a bit of a pet peeve.
Can you tell us about QLisp?
Well, QLisp was an effort by John McCarthy much later in life to redesign Lisp specifically for high-performance computing parallelization from the ground up. So it wasn't just a parallel like an extension to Lisp that supported it, like L-Parallel is. It was an actually like from the ground up. Concurrency is a first-class property of this Lisp dialect.
What's the concurrency model that QLisp uses?
I forget. If anyone wants to look up and tell me, that would be useful for everyone, I think. Anybody have a phone handy? Anybody? Are you looking?
Which model is this?
Well, Termite is after this, like Star Lisp. I would expect, because QLisp is like around the time of like the like Common Lisp standardization, right?
Yeah, it appeared early in the standardization process.
Yeah.
So 82, 83.
Exactly. I was gonna say it's from that era. I'm not really familiar with it, but I suspect that it's more like Star Lisp, which is very parallelism oriented and kind of the idea of dispatching many parallel functions, but like a lot more focused on well things have to be pure and restrict how things communicate.
Which maybe is better than model?
Well, it's the model we're rediscovering of it in functional languages now a lot of times.
But also a better model for quantum computation. So like a prologue, as opposed to like a new mechanic. Interesting.
Like, I could see. So, and see with Nintendo as well, actually, like, that whole idea that, you basically, at the language level, you don't have control over, kind of execution order, evaluation order, things like that. I think the same way.
Yeah, I mean, to my knowledge, there are not many formalisms for quantum computation that are separate from quantum mechanics. The quantum Lambda calculus is a bit of an exception in this regard, and it makes very strong assumptions. There are several other quantum programming languages other than Gripper. One of them is just called QCL, Quantum Computing Language. It's based off of C and C++. Very imperative, everybody gets the job done. And there's a handful of other experimental languages. I don't think any real software has been implemented in them. One of the exceptions of Quipper is that people are writing real quantum software right now, and they're at the scale of real end user software, and not just toys or experiments. Yeah.
My ignorance, but what kind of hardware is available?
Currently, to get the best performance in the simulation, you want access to a university supercomputer and parallel compiled Haskell.
Run out of GPU?
Huh?
Can you run out of GPU?
Yeah, you can if you tweak it a little bit. I don't know that you get that much of a performance boost because it's not doing any
But it's all lazy. It's lazy evaluation to be able to look statically, figure out, okay, this part chunk we can set in GPU, but it's like, where's the demand in that? Because ultimately you're just providing a faster simulation. But what everyone really wants is actual quantum hardware.
Yeah.
And that's where you're going to really see that the language is going to help.
GPUs.
Yeah. So obviously the lack of a physical gate model quantum computer is holding back research in the industry because it does the same. And other than the D-Wave, which isn't a gate model, it's a special class of computer that's designed only for optimization problems, and it's got its own, programming paradigm. So that's a different problem altogether. But yeah, once we have the hardware, things will change, and then the languages will really be put to the test. But Gripper is notable for actually being able to write real quantum software right now. And nobody really expected that to be possible until we had quantum computers that you could, at least bring to an office instead of like a huge warehouse or data center somewhere.
Is it having trouble connecting?
I'm trying to reconnect to that. All right. So a very important question about quantum computation is, how can everyone get to use this? Because even with the quantum Lambda calculus, it's a huge step forward from the Dirac notation for the theoretical computer scientist, but for the average programmer, it's still a bit much. But as it turns out, there's a very, very new book that came out 2 months ago. Dan actually sent me the link to it to check out, and it presents all these, quantum algorithms in plain first-year linear algebra, and make it so accessible that it's almost embarrassing that nobody else wrote this book first. And it's even model independent, so it doesn't rely on the quirks of the gate model or the newer circuit model. And you can even describe both adiabatic and gate model quantum computing with it. And this book actually goes through in detail all the major quantum algorithms that even if it's proven that we can't implement them on a physical machine, they're still interesting from a mathematical perspective because they used to be intractable problems that we thought could never be solved, and now we have, at least mathematically, algorithms that can solve these problems. And it's actually not very expensive either. The hardcover is only $40, which is ridiculous for an MIT press book. Really, really good deal. So if you're not familiar with like the advanced math in Selinger's paper, I would recommend you at least read this. It will give you a much clearer picture of quantum computing as it stands now, as a whole. And some links for you guys to write down if you're interested. Make sure you actually do download the paper. You get the Quipper package from Selinger. And if you're interested in a quantum common Lisp, you can always join my Blackstone project. And that's all. All right, so I guess everyone just ready now, freely? Relax. I guess
Yeah, so there's still more food.